Hey guys, what is up? If you can hear me, this is the stream that we're gonna do very soon. So I'm gonna send out the link, and this should just work. So I'm gonna send out the link. Okay. That should work. Yeah. Okay. So we're gonna be doing Kickstart today, as the title says, and after that, I'll change the title to whatever else we're doing, because people voted for this, and yeah, we're starting with Kickstart. That is what people wanted. So let's have that happen. Quick setup stuff. I already did the thumbnail this time in advance. So that is nice. And yes, I use Light Theme in Discord. Go away. Hey, Golan. Yeah, fine. Okay. So we're going to start this, I guess, whenever you guys are ready. Actually, I need to, yeah, get this set up on my phone because that's my OP setup. Okay. Guess we can just start this at this point. Nothing keeping me waiting. And, no. Okay, we'll close this. And, yeah. I did say hey guys at the beginning. You can see it in the video when this is all over. You just like missed it. Okay, first I have to do the obligatory updating the subscribers because that's like a thing that we do. And if you haven't subscribed yet, you can make this number go up right now at the click of a button. Okay, so yeah. Alright, let's just get into this. I have nothing better to do. So ATM queue. There are n people, a number from 1 to n, standing in a queue to withdraw money from an ATM. Okay. Ascending order of their number. Person numbered I wants to withdraw amount AI. The maximum amount a person can withdraw at a time is X. If they need more money than X, they need to go stand at the end of the queue and wait for their turn in line. Person leaves the queue once they've withdrawn the required amount. Okay. So this makes sense. So basically, the idea is that no matter like what the other people do, say we have 274, then no matter what the other people do, and let's say x equals 3, for example. No matter what the other people do, this person's going to take 1 turn to finish their extraction. This person is going to take 3 turns, and this person's going to take 2 turns, or something like that, however the numbers work out. So all of the people that are going to finish in 1 turn are going to finish first. Then all the people that are going to finish in 2 turns will finish after that. And then all the people that will finish in 3 turns will finish after that. So we can group together the people that are going to finish in 1 turn, then the people in 2 turns, and the people in 3 turns. And these are indices like 1, 3, and 2. And then in this order, the people that are using 1 turn will finish first. And then in the order, the people finishing 2 turns, and so on. And we can use like a map or something because the numbers are big, and we can just kind of do that. So map, we can map like a long to a vector, Oh wait, I forgot my template. What is it? Test case, or just case number. Like that? Yeah. Okay, so read into n and to x, and then we'll use bi to, or actually we can just say map ai divided by x. I think that should work unless I misinterpreted something. That seems right. One, 3, 2, 3, 5, 1, 2, 4. Okay, and yeah, again, basically, like it only depends on the number of turns people take to finish. Okay. We'll read the next task in the meantime. You're in charge of deploying robots to harvest Kikium from a nearby asteroid. Robots are not designed to work as a team, so only one robot can harvest at any point in time. A single robot can be deployed for up to K units at a time, K units of time before it returns. Harvesting can only be done in specific time intervals. What? Oh, we got wrong answer. What's with that? First person withdraws an amount of 2 in their first attempt and leaves the queue. Queue now looks like 2, 3. Second person wants to. Huh. Amount of 7. What is going on here? 4 draws 4 and leaves the queue. We'll start with Kickstart, and then I'm doing this based on how you guys voted, and that means we're gonna do the div 3 next. Yeah, around 674. That will be after this, I guess. Okay, why is this wrong? Something's going on here. So map from a long long to a vector of long longs, and then read into n to x for I up to n, read in the number, and then sorry, there's a bit of lawn mowing going on right now, I think. It's kind of loud outside. For camera, not really anything I can do about it though, I think. So for pairs of long longs and vectors of long longs, then for each number, print it. Oh, I guess it should be ceiling. Oh, that kind of makes sense actually. Yeah, because if something's exactly the ATM amount, it's actually going to cause problems for me. So this should be the ceiling, not the floor. And this is a trick to do that. We just add x and then subtract 1, and then we can turn, floor division into ceiling division. Yeah, because it's supposed to, okay, that was my mistake. It's supposed to round up because if someone's like, if the ATM amount is 2 and the withdraw, like the amount they need to withdraw is 2 and the amount they can is 3, then like it's still going to take them 1. It's not going to take them 0. So I don't understand this problem. Are we supposed to harvest the whole time? Okay, that is correct. Okay, what's with this one? I'm kind of a chess fan. I mean, I kind of just do it for stream because some people seem to like it, but I'm very bad at chess. I'll be honest. So is it like required that we cover the whole all of the intervals? I guess that would be what it is. Harvesting can only be done during specific time intervals. We want to harvest all the Kikium we can. First line of each test case. So we have 2 intervals, 1, 6, and 10, 11. Oh wait, 1, 6, 1, 5, 8, 9, 10, 11. So it'd be like this, like 1, 5, 8, 9, 10, 11. And then what they do is they put a robot here, and then they put like another robot here or something. Or they put this robot here, and then they put another robot here. Okay, so first we can just do the basic stuff like read in the intervals. Whoa. Cn to n. And once we do that, I guess it's kind of greedy. Like, there's no reason to not make each robot last as long as possible. So, we might as well do that. And okay, there's a very dangerous susceptibility to off by 1 errors here. So my idea is basically, say we put some robot down here. Then if it doesn't cover the whole interval, like say we put a robot here and it's like 1. If it doesn't cover the whole interval, we have to put another one down and another one down until we get to the end of the interval. So that part's necessary. But then like if we have something here and say it like kind of overextends, there's no point to start another robot here when we can instead start it here, have it cover the same intervals, and in fact even cover more. So there's no reason to start a robot in a gap. Instead, we can start it at the beginning of the next interval. That is kind of the idea that I have. So we can do like start equals, or like cur equals p0.first, and then answer is the number of robots we need. We start off with 1, I guess. Hi Gabe, what's up? You're doing Kickstart. You're probably gonna beat me at this point. Didn't you like solve everything? Okay, so Actually, we can do it like this: p0.f plus k, and then so what we're gonna do is we're gonna store the end of the current interval that we're at. That is, we're gonna store this point, and then if this point doesn't extend past this interval, then we have to put another interval down. And then at the point where this point does extend past, then we can move on to the next interval. And because the intervals are disjoint, this just like works, I guess. So like we can do something like, oh no, actually, there's some way to implement this. If cur is less than yeah, I do watch him sometimes. He's entertaining. If cur is, I think it has to be strictly less than the endpoint, or it has to be less than the endpoint minus 1, I guess. They have some weird thing where they exclude the endpoints for some reason. So then we need to find out like how many intervals we need, and the distance we need to cover is p0 or pi, not p0. pi.s minus 1, and then that divided by k, because that's the intervals we can cover. And we actually need the ceiling of this, so this is plus k minus 1. Then this, I guess, minus cur. This is weird. Equals max cur minus k. This start thing means that we don't like if this interval ends here, there's no point in starting another interval here. We might as well do it here at the beginning of our new interval. So this would be the maximum of the current endpoint we have and the beginning of this interval. And then we calculate the distance, and then we need that many more intervals. Then start plus equals. It's kind of sketchy. And yeah, I guess that's it. I'll check if my math is right on the samples. I'm too lazy to figure it out right now. Floating point exception. Oh, because we didn't read k. That makes sense. Alright, 3 and 7. That's terrible. What? Okay, what's happening here? Where is it increasing? So in the beginning we have 2, and why is that the case? Because it should be it should be the interval 1 and 5, so that shouldn't even enter that if condition. So 1, 6, 8. How? How is this 8? What have I done wrong here? What? Let's just. Do I have to print the intervals? What am I doing? How's this going so wrong? So 1, 5. Okay, 6, 4, 1. Okay, that part's right actually. 1, 5, 6, 4, 1. Then. Oh, I see. This stuff was on the case number, so I missed that one. Fine. Okay. 8, 9, 6, 8. Oh, I didn't even. Oh, this should be cur. Whoops. Cur equals start. Okay, screw this whole thing up. This should be start here, because that's where we're going to start the intervals. Then ans plus equals dist. Cur equals the starting point plus the distance times k. That is, distance is the amount of intervals we need to add. Alright, so I guess there's some off by 1 errors here. Although at least we have the intervals right now. So we're going to get 1 and 2, which is not good. Don't actually know how that happens. What? I'm thoroughly confused. So 6, 4, 6, 8, 8, 10. It actually extends the interval and starts at 8 for some reason, which I'm kind of confused about. So the distance is the ceiling of this. Maybe we just need to print this. I'm gonna put this in my test case file. Man, we're struggling with these problems today. I don't know why. It seems like I've always been doing worse on stream than I normally do. Because we crushed the div 1 yesterday, and then now we're just like struggling on this B. Just kind of changing, I don't know. So why does that like round? What is any of this? So 8 and 9, which means it has to. I don't know why they make it exclusive. It's like a weird thing to happen. Maybe it's not -1. It might just be. I think they phrased it weirdly, but like it's like a different kind of time. Okay, I definitely don't trust that. So let's make sure we're doing everything right here. So this should be 6, 4, 6, 8, 13, 10. Yeah, we begin the interval. The next interval starts at 8 and ends at 13. Perfect. And the other one is 1, 2. So it starts at 2, ends at 3. Then we start another one. Then we have to start another one. So all of those get their own interval. Okay, that's weird. I guess I was kind of thinking of a different form of time. What I was thinking for some reason is that time is like this, where this is like 2, 3, 4, and 5, and then like this is just excluded. But time is kind of more like this, where the endpoints here are 2 and 5. Yeah, that kind of makes sense. Time is supposed to be not discrete. And then the 3 points here are like that, and then you have 3. That's what it should be. So I think my math may still be wrong, which would be sad, but this could be possible. I'm not really caring about wrong answers. We're just kind of getting them right. And I'll go over like solutions formally at the end, because this is kind of informal and just like talking it out. Okay, let's just try it. Submit first, think later. That is a terrible way to do contests, but it doesn't matter in this case. So if we need a new interval, then the start is wherever it is, and then the distance is the amount we need to cover, and the intervals we need to cover it, and then, yeah. Then the answer, we add the answer, we add to the answer the number of intervals we need. Yeah, I'll do the div 3 after. Okay, we got that one. If you wanna know what I'm doing, check out this community tab in general. Check it out in general, and yeah. So 674 is the next one, and I'm gonna be virtualing that one. There's a lot of lawn mowing going outside. I'm sorry for that. We're doing both. It's okay. We'll get to the div 3 after this. It's gonna be a weird way to. It's gonna be hard to title this video because we're doing 2 contests at once, but we'll figure it out. Okay, it's a single-story building in the shape of a large equilateral triangle. That triangle is made up of many smaller, identical equilateral triangle-shaped rooms, and the side length of the museum is S times the side length of one of the rooms. Okay. So we can treat the rooms like 1 and then just have S be whatever it is. Each room has doors connecting it to all of the rooms with which it shares a side. Each room is identified by 2 numbers, the row of the building it's in, followed by its position within that row. Here's an example of how the rooms are connected and labeled when S equals 3. Sure. Wait, what? Oh, okay, yeah. So it's in the row and then the position. Like, kind of like XY, but kind of weird. Alma and Berth are artists who are painting the rooms of the museum. Alma starts in one room, Berth starts in a different room. Each of them has already painted their starting room. C of the other rooms of the museum are under construction. Neither Alma nor Berth is allowed to enter these rooms or paint them. Alma and Berth are having a friendly competition. Playing a game, okay. So if their current room is adjacent to at least one unpainted room, they must choose one of these rooms, move to it, and paint it. Otherwise, they can't move, and... Am I officially eligible? Yes, but I think so, I don't know. But the time, it was like quite late, and I wanted to sleep for the Div 1 round that was happening right after that, so I decided not to do it live. Okay, so number of rooms painted by Alma, number of rooms painted by Berth. We want to find the best score, okay. So I think it's kind of like the players are playing optimally kind of thing. And regardless of what Berth does means that, like, it means that we can assume she's playing optimally, I think, because one of the possible cases is the worst case where she does play optimally, and in that case, like, that's the one we have to handle, because that's going to be the worst case score. So how big are the constraints? What the hell? Jesus. S is 6, okay. In Python, the time limit is wider, but it's also slower, so there's like a trade-off for that. How big is the time limit, actually? With 40 seconds per test, there are 100 tests, so it's not like we have 0.4 seconds per test, I guess. Okay, how does this work? T test cases work. So each line begins with 6 integers. S, R, A. So each positions and then the number of block cells. And then it tells you the block cells. So how many cells are there? There's like 1 plus 3 plus 5 plus 7 plus 9 plus 11. So there are 36 cells, which is too many to brute force, sadly. But in a sense, it kind of doesn't matter, I think. So each player can move at most 18 times. Maybe it is brute forceable. So each player can move at most 18 times or something. And then... Okay, too many to brute force naively. I don't know. This seems like a very weird setup that we have. And we can model as a graph where some of the cells are just blocked, and then on that graph, no, it seems like the play for one player is to kind of like cut off the opponent so that they're forced in their own thing, and then the other player can do what they want. What are these constraints? So c is less than or equal to s squared minus 2. Why? Oh, okay, yeah, sure. Ri, s, yeah, these are all constraints. Ri, pi. What is this? Oh, it's just that they're all unique, I guess. And they're in sorted order for some reason. I don't know why that's necessary, but okay. This is again a very weird setup. I'm not sure what to do here. We got people tuning in for the lawn mowing. So see, the other rooms in the museum are under construction. Fine, fine. Do I got this? I don't know. I know you got this, Gabe. Gabe also solved it. That's why he's confident. Solved in like 5 minutes or something. Some genius amount of time. I mean, okay, we can brute force the subtask where s is 2, because that's simple. You guys aren't with me? Okay, fine. I don't like you anyway. Like the blocks? No, the subtask's not interesting. We'll just do that. That's just something you'll do and then be done. I don't know if DFS will work. It's kind of like a weird DFS where they have to do certain things. So like the absolute worst case is when the entire graph is unblocked. And then in that case, there's like a lot of things to do. Yeah, for the subtask, you kind of just like do things. It's not that interesting. Like if one of them's in the middle, then they can get another cell, and otherwise they can't. Otherwise, it's the first player that has free reign of the middle. It's very weird. But also, everything is very small. Yeah, the memory limit's usually this big. But like the bounds are 36. I don't think memory is going to be the issue here. Actually, it might be. I don't know. By brute force, I mean the dumb thing, not the smart thing you're probably thinking of. But I mean, there are other things we can brute force too. Like, For example, the number of turns they make. We can say we want player A to make a bunch of turns and then player B to make, like player B can make 5 turns, I don't know. Maybe stuff like that works out. It's like the side cells are adjacent to 2 other cells. What does it look like with 4? And it's even weirder. Some things like bitmask or something, I think. Whatever works, really. Like a bitmask of the cells that are filled in, and then you figure out whose turn it is, and then they can just like move somewhere else. It's kind of a lot of information you need, actually. Okay, so we can say we're trying to maximize the score, I guess. But yeah, it doesn't work because 2 to the 36 is too big. Like, way too big. Doesn't even fit in memory. Yeah, it's going to need even more information, actually. That's true, that is a problem. It's like way too much information. Gabe, you telling me we just brute force it and there aren't that many states? Seriously? That's annoying. Is that really the intended solution? And actually, there are more than 2 to the 36. It also depends on like their positions. That's so annoying if that's the intended solution. Why would they do that? How do people solve this? Do people just like, do they just see this kind of stuff? Because I definitely would not have. 346. Wow. Yes, they did. That's kind of sad. I don't have intuition. I didn't even think of that. That's kind of weird. Should ask Gabe. He's like Ors. something here will be. How many states are there? Like, why aren't there that many? I guess it's like you have a sequence of positions. Either you have 1, 2, or 3 places to go, and actually, in a lot of cases, you only have one place to go. This is like USCO training vibes. Oh god, don't like this kind of thing. I guess that's what we're doing though. Alright, we're just gonna make a graph out of this because I don't want to like do the other thing. So wait, no, that's not a thing we can use. Apparently y1 is like some STL variable or something, some function, so it's not a good idea to use that. C into K, and then like I gotta like do some weird stuff. So what this function is going to be is it's going to be like the ID given a row and a column. And the way we can do that is like, basically we have 1 cell in the previous row, then 3 cells in row 2, then 5 in row 3, and so on. The sum of these is like, the sum of these is just the squared numbers. So this is 1 squared, this is 2 squared, this is 3 squared, and this is, or squared, this is 4 squared, etc. So if we're on this row, then we know there are 4 squared rows before it, and then we can just add the r times r plus like whatever we have is like the row or the column, I guess. So it'd be that, and then -1, 0 indexing, some lazy. Okay. Actually, these all have to be global anyway, whatever. So it's like, make the edges now. We can do it for every test case because it's like whatever, it's a small number of things. J equals 0, J is less than 2 times I plus 1, something like that. 2 times I plus 1, I guess, yeah. Then, so we need to add the edges. If we're not on the bottom row, I plus 1 is less than n. Yeah, it's even weirder than that. Okay, so the we can treat it like this. So we'll ignore the squares that are bottom up, and then we'll only consider the squares that are like pointing up. And then we'll just add the edges from the pointing up ones to the not pointing up ones. So if I plus 1 is less than n, and so the pointing up ones are the ones that are going to have odd indices, which means 0 index, they're going to have even indices. So if I plus 1 is less than n, then they have an edge with the thing below them. Is f going to be even worse than this? That's going to be annoying. So it'd be like edge id I plus 1, j plus 1, and then id of I plus 2, j plus... Let's see, so this is going to be exactly 1 greater, so it's going to be j plus 2 as well. Then, if we're not at the beginning of the row, we can add an edge between this and the one before it. So if I is greater than 0, edge id I plus 1, j plus 1, I plus 1, and then the previous column. This should be j, not I. Then if j is less than whatever this is, in 0 indexing, this would be 2 times n, I guess, or 2 times I. Then what would it be? I plus 1, j plus 2. Then we gotta like do some more stuff. And what's the more stuff we gotta do? This is fun. I love this problem already. Isn't it so fun? Okay. I guess we can do like memoization or something to make sure we don't visit states multiple times. Is that even necessary? Probably. Maybe? I guess it would be a good idea to do that. Do we need to memorize? I don't even know. Don't even need to worry about memoization? Okay, fine. So bool vis 50. Okay, so now we just write like the bulk of this. It's cancer. And yeah. So DFS with the starting cells. ID A, B, ID C, D. And then the score initially is 0. Thanks, Gabe, because I probably wouldn't have... This is not something I expect in a solution. This is something I expect from stuff like use code training. I have tried dark mode. It makes like the whole screen feel cramped, and I don't like how it feels. A, L, B. These are the positions. Maybe we need int. I don't know. If it actually becomes a time issue, I'll switch everything to int. But I'm so used to long that like it doesn't matter. It should be vector long, so I don't use that template anymore. So we're guaranteed that the starting rooms aren't dead, I assume, because otherwise they wouldn't be there in the first place. Yeah. Yeah, these starting rooms aren't blocked. Okay. Now, guess we also need the turn. 0. Oh wait, this. These are guaranteed to be visited. So what we need to be able to do is to like skip a turn, but not like infinite loop. I guess we can just write some code and copy it. Move equals 1. So move basically means if they have a turn, then do it. Ants equals max ants score. And actually the best score we can get is... No, wait, never mind. The final score is if neither of them can move, I guess, because they can't end the game. Yeah. So then DFS next B turn not turn score plus 1. If not move, then we'll assume B is the one to move, and then we'll just try that. And we'll just kind of copy this code a bunch of times. And it's just gonna work, I guess. Then what is this? So this is A next. And we have to undo it. And if neither of them can move, then the game is over, and so we are done. Let me just kind of do the same thing for the other turn, I guess. I don't even know at this point. You just like switch these. This is so annoying. Move equals 0, then for each next thing the person B can do, just like check it. This should be score -1 because now the person B has a turn they made. I guess that's it. Nice. I guess I've done something wrong here, for sure. For the next possible thing... Okay, wait, what? Did I mess up the edges somehow? Printing a new line. just has to print, just to flush the output. I'm reading the input wrong. Okay, so 0 has no edges, which makes no sense at all. Great. How old am I? 17. High schooler. So is Gabe. Should be proud of Gabe, he's better than me. What are these edges? Oh wait, this should be K, not N. Maybe that's the issue, we thought everything was blocked. The edges are still messed up though. Why are the edges still messed up? I am not in college now, no. What is this? 211210. That doesn't really make a difference. What matters is that we're doing these edges wrong. Somehow. And so I plus 1 is less than n. 0 has no edges. That's a problem. And 1 has an edge to 5, which makes absolutely no sense. Kindergarten, yeah. I was born with a keyboard, and we just took it from there. Gabe's gonna be the next tourist. Actually, he already is tourist. If I plus 1 is less than n means that... Like, what is happening here? Are we iterating through the things, right? Yeah, he actually trained both Neil and Scott Wu, so he's like above them. Like they were his apprentices. So 0, 0, okay. And then if I plus 1 is less than n, which it should be. Did I like screw this up somehow? What have I done here? Why is this not like adding edges to both? Maybe I screwed up ID. Okay, so this is 1, 5. 1, 5. Oh wait, this should be r minus 1 times r minus 1. Whoops. Because that's the previous row, not the current row. We want the number of cells before the previous row. Okay, now we actually have this right. So 0, 2, yeah, 2 has everything. We set up the edges right. Okay, I don't trust this, but we're going to submit it anyway because I don't care. Comment all this out. How? What? What is this? Why does this happen? That's a weird thing that I don't understand from Notepad++. Okay, let's just submit it. Who cares? I don't. Like Gabe actually, he genuinely like mentored those guys. He is a legend. Gabe is the unseen god behind it all. We should get the first subtask at least, at the very least. No, why would I prove my submission? That's like too much work. Oh, we get wrong answer. Okay. Which means we do finish in time, as Gabe said we would. Now, proving your solution is overrated. Like, mathematically, like if you mathematically prove things every contest, that's like so much time that you're gonna spend. I mean, sure, you can back your code up by like intuition or whatnot, but I don't think it's a good idea to like do a rigorous proof every time. I mean, some people do, and that's fine if they want to do that. Then that's like preference, but I don't. Yeah, my intuition said nothing to me about the few states we would have, but whatever. Let's see if we screwed up any of the other edges. Okay, let's try 3. Yeah, and I don't know why I got this wrong answer, but I'm pretty sure it's because of stupid coding bugs. So 1, 1, and let's say 3, 5, and then 0. I just want to see the edges that are created here. Oh, wait. Okay, so 0 has an edge to 2, 1 has an edge to 5, 1, 2, 3, 4, 5, 5. Okay, perfect. Because we're 0 indexing, and to 2. 2 has an edge to 0, 1, and 3. 3 has an edge to 7 and 2. 4 has an edge to 5. 5 has an edge to 1, 1, 4, and 6. 6 has an edge to 5 and 7. 3, 6, and 8, and 7. Okay, so the edges are right. What else is wrong? So what we did was we started everything here, which means that I guess the optimal strategy here is to do this, and then this, and then this, and then this, and then that. Yeah, okay. So 2 makes sense here, actually. What if we did it in, if the first guy started at 2, 2, then the answer should be 1. It's not 1. Because I didn't copy it? Okay, yeah, answer should be 1. Okay, so the edges are right, I guess. So just like the logic that's screwed up. Okay, let's say stuff is blocked now. So let's just like totally block out birth. Screw birth. 3, 4. Oh wait. And the answer here should be 4. No, 3. 3 is right. Okay, let's say we start at 2 and 3. What? Two and 3 answer should be 4. Yeah. Okay. Alright, I'm gonna look for coding bugs then because there's no obvious issue, and I zoomed out somehow. So void solve. Was this my old font size? Guess it was. Print the case number, fine. So read in like the input. The input is important. Then we just like set it to dead. Did we reset everything? So dead. We clear all the edges and we set this to whatever. Yeah. I mean, it's kind of like, yeah, it's kind of like chess. It's just the same like intuition sort of thing. Get intuition and then you believe in it and then you trust it and then it fails you. That's the cycle. And it's kind of sad when it fails you, but most of the time it doesn't. If you get it to be good enough. And at the same time, you just like get better accuracy in terms of like not making dumb typos, like switching I and J and stuff. It's like a better process of thinking in general, at least in terms of CP. Not maybe not in general. Okay, so clear all the edges. Read in the stuff. For I up to n, for the even-celled triangles, if I think the edges are right. We did the edges as I expected them to be. So I will trust that. Set this to dead, as in if they're already killed at the beginning. And we also set the visit of the beginning cells, then we DFS, and just like print the answer. Okay. Pray to Bessie, yeah. Okay, let's screw over our main character now, whoever this is, Alma. So we get 1, 1, and then 3, 5, and then 1, and then we block off 2, 2. Are we capable of printing negative scores? We are, okay. I think I messed up the guarantee part, actually. Yeah, I messed up the guarantee part. That's a thing. Okay, this is stupid. I shouldn't have done this. It's like a fundamental error with what I'm doing. Because we're solving for the best case with Alma and the worst case with birth, which is not good. Wait, why am I taking the maximum? It should be the minimum. Like, I'm doing this entire thing wrong. It should be the... Well, it's not exactly the minimum, it's like... It's kind of weird, because, like, if we have birth completely blocked off, then Alma can do whatever. And they'll, like, win. So we can't entirely take the minimum, but we can't take the maximum either, because that assumes birth is, like, worse. So there's some better way to handle this, I'm sure. We have to, like, build the tree and then do minimax or something? Yeah, we have a genius supreme leader like Ben Q or something. He's good. I guess we can solve it like that. Trump equals Ben Q? What? Wait, what did I miss? How did we get to that? What? Alright, let's refactor this a bit. I guess we do have to do it like minimax. And that's kind of like a theoretical thing. So if it's a second player's turn, they want to maximize the amount of IOI. I don't think that's happening. So if neither of them can move, then like... Oh, I see. I see what you mean, yeah. Kind of lost the context. So if neither of them can move, then it's just like something, so it should be this player just moved, which means this will be 0. So we kind of hard code this one in 0 and 1. And what that lets us do is, if we expect the second player to move and neither of them can do anything, then we return some like large number. Yeah, because the second player is trying to minimize, and otherwise, the first player is trying to maximize. But then we run into other issues. Oh wait, no, it should just straight up be score. Like, what am I doing? Yeah. Because this is the state they're at. It's the final evaluation of the position. Okay, so in this case, this dude's trying to maximize it, so we'll make it small. Cur equals max cur DFS. And otherwise, cur equals 1e9 because we're trying to minimize it here. Let me do the exact same thing, kind of. Yay, games! I love these problems. So fun to never believe in your solution. Oh, come on. Now it's -4, which does make more sense, actually. Okay. I guess we get that right now, and then this should still be 2 and 0. Screw it, we'll submit. Just testing on that. Don't really care. If we got some bit of casework wrong, we'll just figure it out. Then we have the last problem, which I heard is very annoying, so I'm not looking forward to this. Okay, well, we got it eventually. And so that solution is to literally do like the naive thing and just realize there aren't that many states. I don't know how many states there are. Maybe we can figure that out. But at this point, like, whatever. It lets us see code, right? Like, once we... Yeah, okay. So maybe we can revisit that later and actually hard compute the number of states. Send or help? Well, I just wouldn't. I mean, I've never even thought of using those variable names. I mean, you also never need a variable name like F0R or something. Those are also issues. They're just not that big of an issue. I do run into trouble with S and T sometimes, though. Like, I use S for sum or something. Then I kind of have to declare it again, which is weird. By the way, I highly encourage you guys to adopt the solve function structure. Because when you have multiple test cases like this, it's very easy to set something up where you have to only return instead of do some like C into T and then some like. And then when you're done with the test case, you have to do some setup like. And then if not possible, print no, and then like go to finish or something. I think it's possible, but it's so much easier to just type return. And then, you know? Yeah, get the solve function, guys. By the way, my goal today is to hit 1.8k. We are kind of close, but not really close. We still have 22 to go, I believe. So, come on, guys, get us there. I think we can do it. Okay, no way. Beyond that, let's do Yeatsy. Because why not? There are N dice. No, it's not that I'm overs that I did the whole thing. It's that I'm like stubborn. Like, there are some helpful things in the later sections, but it's much better to just like practice whatever you're actually trying to do. Almost very bored at home. Like, I would have been better if I had just practiced some gold problems or something. Almost very bored at home. She's invented a new game. N dice. Each number has the numbers. Okay, I can't read. From 1 to M written on it. Whenever she throws a die, it has an equal probability of landing on each of the possible values. All the dice in a row. Goes to the dice one at a time. Reroll a die as much as she wants. Puts the dice into groups. All dice with the same value put in the same group. The final dice results are 1, 6, 7, 7. The dice will be put into 3 groups and ordered as follows. Wow, okay. That's great. What is the expected value of the total number of dice rolls it will take to win the game, assuming she plays optimally to minimize this expected value? Jesus. And the negative 6th error, okay. So if there are exactly k groups and the ith group contains exactly ai dice. So it doesn't matter what is what. Oh boy. I can already tell this one's gonna be fun. How long is this contest? I'll do this until the contest would have ended like normally. What's the round duration? I guess just 2.5 hours. Okay, well, yeah, I love combo, and I love expected value, obviously. As you can hear from the tone of my voice, they're both great. 3 hours? Oh god. I'm gonna go for 2.5. I can't do this problem for an hour and a half more. Definitely not. Unless I do get somewhere. Maybe. Maybe. That's doubtful. Whatever is happening here. What is happening here? I mean, firstly, it doesn't matter what the actual values of the dice are. It's just whatever groups we have. So when you roll a die, I guess you start a new group, and either you start a new group or you extend another one. So if you like extend one that you don't want to extend, then that's bad. What's the constraint on A? Okay, it's just M. Yeah. Great. This is where the stream gets rough. Okay. Feels like the only amount of explanation I did for that one. So let's say you already have some like groups built up. I've never used Twitch before, and I probably could. Doing both simultaneously will be weird. I don't think people do that, so... I don't know, YouTube's comfortable. What are the benefits of Twitch? So I guess if we have a group, right, then 3, 6, 2, 1, 2. Minimax is theoretical comp sci more like. It doesn't... Like, this is the first time I've ever seen it. I don't think it's that necessary to learn it properly. It's more about, like, game theory, I guess, and stuff. Like, basically, Minimax is a very simple idea. The first player wants to maximize the score, the second player can minimize it. So if all moves the second player can do, they'll take the one that minimizes the overall score. And of all players that the first player can do, of all moves that the first player can do, they'll take the ones that, like, maximize the score. So when you're considering moves for the first player, once you compute the outcome of all of the moves they can make, you just take the maximum. And then, like, you just, the minimum for the second player. Most game theory problems don't require it. It's either like, whatever it is, Grundy numbers or something. Because it's usually asking for who wins, not what's the score they can have. This is like a straight... That one was like a straight theoretical problem they just decided to put here. This one I can tell is not going to go well. Well, everything's like small. That's the thing. So when you have a group that you say is like incomplete or something, like there's some the only thing I'm seeing here is small constraints. I guess that's important for something. It's like a lot of stuff going on. So your role, any given role either has some chance of like doing what you want it to or not. And I mean that's not helpful. So I'm gonna give you consider the ideal groups like something like 1 and 2. And then we consider the initial state, which is like we have no groups in either. We have no groups at all, actually. Then the first die is always going to do what you want. It's going to help you somehow. The first die is going to create a new group. The second die will either add to this group or create a new group. In either case, the second die does what you want. So you might as well keep it. And then the third die, now, it has a chance of not doing what you want. For example, you don't want a new group. The only thing you want is to extend an old group. And at the same time, if we have it that the second die is the same as the first die, then what we want is for it to create a new group. And then let's see how that helps. I mean, the probability of something doing what we want is like, it's like the number of groups. We have a certain number of groups that are like open. That is, they can be extended by some die, and that would help us. And we have some number of groups that are closed. Like, we don't want something to land in their group, I guess. And if we have like x open groups and y total groups, then the probability is x over y. And then the probability of it happening once is x over y, and then the probability and then this takes one turn, and then so we can say it like this. So like kind of like this. So the probability of something happening is, I guess the expected number of moves of something happening is x over y, or no matter what you roll this die, and then either it works here, or you have a 1 minus x over y chance of needing like another EV or something. And then you like reduce this down to the geometric series formula or something. So like 1 equals EV one minus. Does that make sense? I don't think it fits. There's supposed to be some geometric formula stuff here, or geometric series. But oh, I guess it is. Like the initial term is 1, and then it's kind of whack. So if we just solve this, then we get 1 minus x over y. And we just end up with x over y. So then the EV is y over x. Okay, I've never actually done that equation before. Nice. So the chance of the chance of a die helping us out when we have x possibilities and y, or when we have y possibilities and x things that will help us out, is just y over x. And I guess doing the geometric series formula is the same, because the r value is 1 minus y over x, or 1 minus x over y, and the beginning value is 1. Sure, that works. Okay. I guess it does. Yeah, that's fun. Anyway. It's a bit of math that's, I guess it's gonna be required to help us out, but how? The question is how. Yo, what's up? We are failing this problem. That is what's up here. It's basically my plan for the next hour, I guess. I don't know why I'm doing this. I don't know why I signed up for this. I knew this would be painful at some point. Yeah, I'll do the div 3 after this. If you've seen my post, I had a vote, and Kickstart was the most highly voted for, but the div 3 is the next highest to Codeforces? I don't know about that one. I can't do it live because it's like right in the middle of school. I don't know, I might do something else instead of that. I don't know what my plan's gonna be. Is the Div 3 easy? Isn't it like the Russian Olympiad? Everyone hated that one before. When it was the Div 2, like round 6, 40 something. I don't remember what round number it was. 657? I don't know. It was some Div 2. And like everyone hated it because it was hard. Is this one different? Alright, so whatever is happening right now. Yeah, 657 I think is what it was. So this div through is based on round 1 and therefore it's easy. Sure. So one thing we can use in this problem is basically like what's the chances of a die roll helping us out? And so we have like a lot of zeros at the start. We have a lot of groups of size 0. Like we have n times 0, and then 0 times everything else. And for the rest of the things, we got like we have some other groups, and all of them are positive, I guess. So actually, we have a bunch of other ones like 0. Let's think of the first sample. So the first sample has 2 groups and it has 6 possible dice outcomes. And those are both zeros. And then the expected ones are like 0, 0, 0, 0, 1, 2. Where did I practice USCO training? It is the place. And just USCO like in general, I guess. USCO training is... I have conflicted opinions on it. Like, it gets very low quality at the end. Or it's kind of like just like a bunch of optimized brute force. But in the middle, it's pretty good, I guess. Although, whatever you're looking to practice for, practice on that site. Like, if you want to do interviews, don't do a bunch of ad hoc problems, because that's generally not going to show. Actually, I don't know. I don't know how interviews work, but I mean, just practice what you're trying to do. Don't go out of your way to do other things. So, right, here we have this. This is quite weird. I wonder if this is also brute forceable. It doesn't seem like there's actually much going on. Because the constraints are 50, and for partial you can brute force it, pretty much. I wonder if the whole thing is brute forceable. Because the constraints are like tiny again. And we don't need to store the actual numbers. We only need to store the number of intervals we have with 0 of them, and the number of groups we have with 1, and the number of groups we have with 2. And so the thing is, the number of states we have is... I don't know how many states we have, but it's like... I guess it's too many. It might be too many. This is kind of weird to think about. It's gonna be a thing. You're gonna spam the loading screen when I'm like trying to think of something and getting nowhere. That'd be kind of funny, actually. So right now the state I have in mind is some like vector stuff, where a state is the number of the amounts we have of each group, essentially. And it's kind of weird to think about how many states we're actually going to have. Because say we have something whack, like our intended groups are like 0, 0, 0, and 50. But then like we only have 50 states because, or 51 states, because only one group is ever going to be different than what we want. And so if we have something like 0, 0, 0, there should be some worst case here, I guess. Like maybe it's like 0, 0, 0, 7, 7, 7, 7. We have 7 sevens. Then what happens here? Well, the worst case number of states is 7 to the 7, which in itself isn't that bad. But like, even then, there aren't that many states to have. So let's say we get rid of that and have like 7, 7, 7, 7, 22. Then we have one state that's going to be big. Like we're going to have this 23 over here. And then these are kind of small, and then the other ones are kind of small. Like my intuition says that there aren't that many states here. Although I can't trust my intuition, because my intuition lied me last problem. And it said there would be a lot of states, and there weren't. And in fact, I'm not even sure how many there were, but I think... How many were there? Like, how slow is my solution? It was... Does it say the time limit? I don't think... I guess it doesn't, but... It wasn't that bad. Wait, we get 20 seconds here. We get 20 seconds for... Oh, wait, no. Okay, sorry. 100 cases. Never mind. Yeah. So we got 0.2 seconds per case, which is not the best, I guess, but... I don't know, I guess we can go for partial. What would partial even be in this case? Okay, here's how we would do partial. So the state is... The state is a map, which basically stores for each group size, for each group size that we have, we don't have to do all the group sizes, how many of those group sizes we have. This is so weird. Here, let's just do this. This should actually be doubles. So we have doubles here. The final state should be doubles. And somehow we have to like get to some stuff here. Eventually we're going to end up in the final place. Let's just do partial. I don't know at this point. And the state is literally a map. So if mp.find groups is not equal to mp.end, return mp groups. And maps are just going to allow us to do this, I'm pretty sure. I'm pretty sure like there's some comparator for maps, and therefore we can just do this. Maybe it has to be a vector. It doesn't really matter though. This is weird. I've done this once before for like some use code problem where we do some weird DFS, but I'm not sure. I'm pretty sure my intuition is lying to me. There are probably a lot of states. Do we have to sort? I don't care. It doesn't matter. Now, first, hello point equals 0. Oh wait, this should be k. Yeah. And then sort a plus k. So for pair. First, we're gonna check if we're at the end, like if we're done. And if so, then if x.s is not equal to a point break, then if we reach the end, then we're done. Cool. Otherwise what? LO useful equals 0. So now we kind of do the same thing. We basically count the number of groups such that if we add something to those groups, it'll be helpful. And that's equivalent to saying the number of groups that aren't like actually wait. Whoa. Amber alert. Okay. That's fun. It's kind of weird. We kind of want to go backwards through the array. Did you guys hear that? Was that? Yeah, I guess that was loud. Yeah. Sorry, that just totally came out of nowhere. That was an Amber alert. It was like the entirety of everyone just gets like notified whenever there's something like a child abduction. Yeah, my ears are bleeding too. I heard it like loud and clear. Sorry, but yeah, I think you can disable them, but like I don't know. It's useful to hear for stuff like because they also do it for weather and it makes the exact same sound like this is if there's a tornado warning or something, which has happened before. Okay, this isn't exactly the condition we want, I think. It's more like when we have some element that isn't equal to... Yeah, okay. I'll explain how this works later. I'm pretty sure this is right, although I'm not sure. P_sum plus equals x dot second. This should actually be x dot... No, it should be x dot second, right? Yeah. We don't actually care about this. And then it's like useful equals P_sum. Because it's going to be some prefix of groups that aren't... Actually, the groups that are already like filled in, that is, if we add another element, then they're going to be useless. Is going to be a suffix because of like it's sorted. Like if our ideal groups are like 1, 2, 3, 7, and we have groups like 0, 1, 3, 6, then even though these two are equal, wait, actually no, that's not even right. That's not even right, is it? No, it's not. I just like showed myself that I'm wrong here. Hmm. Okay, wait, there's some better way to handle this, I guess. We can do if possible. Kind of struggling to flesh this out. Like, what is the idea here? We need to find the number of groups such that it will help us if we use those groups, kind of. How do we do that? Well, let's make sure this is right first. So this is basically checking if this is the final state, if we're done. And that's asking, what is that asking? Well, it's asking something. It is asking something, that's true. This is kickstart F problem D, by the way, or the fourth problem. If it's possible, return 1. Then here we need to check if it's like, if we're at the end or something. And I'm not really sure how to do that. So we assume the state is valid, because if it's not valid, then like we wouldn't have gone there in the first place, I guess. So we have these things listed out, and we do. then we find out the number of groups this can go to. And either it can go through, find out the number of groups this can go to. And it can't go to any of these groups, so it has to go to this one. So now we kind of like focus on these. And these can't go to any of those groups, so they have to go to this one, I guess. Okay, well, I think what we have to do is like do some iterator stuff, and we want to iterate through the array or through the map backwards. And that lets us do that. So then what time is it over here? Like noon. Yeah, my brain is loading. I don't think it'll ever stop loading. I think that's the way this works. So it's still gonna be some suffix, I imagine. So we look at all of the highest one, and then we say in the array, is there anything higher than this? And if so, then we can use that, I guess. I guess it's possible for that to be helpful, but this to not be helpful. So this group is helpful only if, what is this, k minus 1? So if a point is less than, or if a point is greater than, if the highest element in this like group of 6's reach, I don't know how this works actually, this is kind of weird. I guess either of them will help us. The highest element in this group's reach is better than the group size we currently have, then useful plus equals the count, then point minus equals x dot s. I don't know at this point. So now we can get to the fun part, which is equals m over useful. That's something we calculated earlier. No, I don't have school today. We have some like Jewish holiday or something. My school loves those, so we just have a day off. Yeah, I would not skip school for streaming though. All of the remaining. So it's like do kind of the same thing. It's like just kind of some math, I guess. Remaining plus equals, what would it be? So it's the x.s, the probability of having this be the useful thing. Useful. We want to make these doubles. Useful is a double. No, it's not a double. What? Oh, this should be a double. X.s over useful times. Yeah, I don't know why he would be on my stream. My stream is like worthless, but yeah, props for sticking here, I guess. So remaining plus equals the way we have the chance we have of getting this, and then times oh, actually this is where we do the DFS. So minus MP x dot f plus MP x dot f plus 1. No. So basically we like assume the die lands on this, and then we just move on, and then we undo that change once we do this. So it's return the expected number of moves plus the expected number of remaining moves. It should be 0 actually, because we're done in this state. There's absolutely no way this works, honestly. There's no way this works. It doesn't even compile. Nice. So no match for, huh? Oh, wait, this should be groups. We'll make a new map. What? Pretty sure like none of this program is right. Haven't really like thought much of this through. Okay, yeah. Nice. That's dumb. So we have infinity. There's no praying to be done here. It's already screwed up. Okay, so what's happening here? 0, 6. 0, 5. 0, 5, 2, 1. 0, 4, 1, 1, 2, 1. 0, 4, 1, 2. 0, 4, 1, 1, 2, 1. It's actually right. 0, cout pos is actually right. It's actually visiting the states in the right order. Could this be? It could not be. It doesn't even think this is the end. Great. What's with that? Okay, so I guess it's like, okay. So for we don't have to erase this, I guess. We probably should though. Just for consistency. Yeah. So for I equals 0, I is less than n minus k plus ai equals 0. Then I plus n minus k. And that way the array at the beginning will be padded with zeros. Yeah, spam clowns. I definitely deserve those. What? Oh, I copied the output. Why would it stop there? Huh? Why would it stop there? Should still be not possible. Okay, that's like weird. What's happening here now? So we have a lot of zeros, which means that any one of these zeros should be useful, and some of these ones should be useful too. Oh wait, actually we want to start point at m minus 1. Yeah. So now it still doesn't think these are possible somehow. Well, I was doing something stupid by pasting in the input, or pasting in the output as input. What? How? How does it think that's a final state? What do you mean? What does it mean? I don't know what it means. So like somehow it still doesn't think these are possible. So while x dot s minus minus, if x dot f is not equal to a point, then possible equals 0 break. I understand. What? Why is this glowing orange? What is it doing? Okay. I'm so confused. It should be right. Like, it's just comparing everything to the array. Oh, come on. So 0, 0, 0, 1. What? Oh, wait, this should be m. Oh my god, I'm screwing everything up. Yeah, this should be m, not n. My bad. Again. Because m is the actual number of groups we're going to have, n is just the number of dice. God. Well, it's actually right. That's not something I expected. Guys, it's right. What? It's actually right. Wow. This is not something I expected. Nice. I guess we're doing something right. Let's submit and get the first subtask at least. And then if necessary, we can optimize this. What the hell? I didn't expect this to be right, man. Just kind of like memeing around over here. Just expecting this to like, expecting to have like 2 hours of debugging, but no, it's actually kind of working. So because my constant factor is horrible, it should, okay, what? What does it want? Sample failed, wrong answer. What does it print then? Is it some undefined behavior? Nice! Failed the sample. What happens here? Are we printing some extra debug output? Maybe it has to do with like doubles or something. What? Oh, I forgot the case number. Whoops. I got so confused there. Alright. Let's try it. We should at least get the first subtask, if nothing else. I don't really know how it's going to do on the second one. It might TLE, which is very possible. Actually, it's very, very possible, but I don't know. I mean, there's a chance that it won't. Honestly, this type of stuff, like this type of combo thing or expected value is not my strong suit, so I don't know. I'll do what I can. As long as we're still getting somewhere, I'll keep going, I guess. It's taking a long time, though, so maybe it is going to TLE. Shouldn't take multiple minutes, though. It's taken over a minute, so I don't think that means... It can't be slow, because the time limit's 20 seconds, so if it was... I mean, it could be slow, but that doesn't imply it's slow, because the time limit's 20 seconds. Which means after 20 seconds, it would have just tested. Actually, after 40 seconds, it would have tested. What is going on? Okay, well, I guess we can look for ways to speed this up. I don't know. Oh god, I just realized something. We forgot to clear the map between test cases. Oh god. Okay. Alright, it's definitely gonna TLE then. Actually, it's gonna wrong answer, I assume. Oh boy, that's fun. Okay, wait, is there anything else stupid I did? So, like, we're doing memoization, that's fine. Case numbers, okay, so now we do clear the map. Okay, let's try, wait, how did it get that right? Let's try it again, one more time. Wait, I'm confused. How did it get that right? It's like not... Oh, because we don't do memoization at all. Wait up. What am I doing? Oh my god. We just straight up don't do memoization. This is such a joke. Guys, spam clowns at me. This is stupid. Spam clowns. I need to be spam with clowns for the stupidity. Any clowners in chat? Whoa, we got it. Okay, that was quick. Wait. That was it? That was it? That was it. That was like instant. That was instant. Yeah, okay. Okay, so now, because people may have missed the stream, what I'm going to do right now is just explain all of my solutions. And this is sort of for retrospect for also the purposes of the video that's going to be explained. And yeah. Okay, it's kind of not GG because I needed Gabe's help with this problem. I genuinely would not have gotten it because I didn't expect it to be like that. So, although I got this one on my own, for sure. This one's fair game. Alright, so ATM queue goes like this. I'll assume you guys know what the statements are, because I don't really want to read out statements. It's kind of a waste of time on stream, so let's just not do that. Wait, did I leave I left a link to the contest in the description, right? If you don't know what I'm doing, you can, yeah, check the description for a link to the contest, because it's right there. That part should be fine. Okay, yeah, GG, we got it. We got the last problem. So this is ATM queue, and I'll just say that. So let's take one of the samples. For example, we have the ATM amount is 6, and we have 9, 10, 4, 7, 2. So here's what's going to happen. The first person's going to go up, and they're going to subtract 6, so now they're going to have 3. And the second person's going to go up, and they're going to subtract 6, and now they're going to have 4, and etc., right? But each person can only subtract like the ATM amount that it lets them, which means that solely based on the amount they start off with, it's going to take them a certain number of turns for them to run out of like money, or to, I don't know, whatever the goal of the problem is, for them to withdraw all their money. Yeah. And specifically the number of turns is like, it's like the greatest k, if k is the number of, x, okay, x is the number that's withdrawn in the turn. So it's the largest k such that kx is, smallest k such that kx is greater than or equal to ai. This is also the definition of the ceiling of ai over k. So each person, it should be, I'm messing this up already. It should be k is equal to the ceiling of ai over x. So this is the number of turns it's going to take everyone to finish their withdrawals. So for example, this person's going to take 2 turns, this person will take 2, this person will take 1, 2, and 1. So in order, the people that are going to take 1 turn are going to finish. So, and all of the other people aren't going to finish. So we can say that everyone who's going to take 1 turn is going to be done on the first turn. And they go in the order that they're lined up in. So in the first turn, people's 3 and 5 will be done. And then the next turn, people who take 2 turns are going to be done. So in turn 2, people that take, how am I out of space? 1, 2, and 4 are going to be done. And so if we had some other numbers, like for example 6,000, then this guy would take 1,000 turns to finish. Poor guy. And so we could skip all the other numbers, and then we would have a 1,000 here. Okay, I technically didn't solve the third problem, so it's not that fair to say that. I technically didn't solve it, but yeah, I can. If the scheduling isn't too bad, I can try. So the people who take 1,000 are going to be last. This will be person 6. And we can use sort of a map or like some sort of structure that will store these to kind of ignore the rest of these. We only go through the values where at least one person takes that amount of turns. And the way we can do that is with some sort of map or something. We can map turns to like a list of the people with those turns and then go through that map in order of turns. and then we make sure that they're sorted by their initial positions, and then we just print those positions. Okay, that's problem 1. But yeah, I did not officially solve problem 3. I mean, I wrote the code and stuff, but it was like kind of needed help for that one, so it wasn't totally fair. Alright, this is metal harvest. What was this problem again? Oh yeah, it was this one. Okay, so in this one you're given a list of intervals and you want to like put a bunch of disjoint intervals down to cover these intervals. All disjoint intervals must be of the same size, and all of these intervals are also the same size, so it's like working out. You want to find the minimum number of purple intervals you have to add to cover things. So this is basically just like casework and math, just like kind of the other one. Actually, no. But it's a lot of casework, kind of. So the basic idea for this problem is like you want to put down intervals as late as possible. There's no reason to put down an interval earlier because it's going to cover like strictly fewer area that you care about. For example, if I put this interval here, then it's going to cover half of this, and this whole beginning of the interval is like wasted. But if I put the interval here, then as much of the beginning of the interval is used as possible, and we're going to have some like stuff on the end too that could end up being more useful later. So that's the basic idea. At every point, put down an interval as late, like make its starting point as late, as far to the right as it can be. And so now the way we can do that is, well, if we simulated putting down all intervals, it would work, but the constraints are 10 to the 9th, so it would like take too long and we would probably TLE. So that's not a good thing. What we instead want to do is be more efficient about it. So the first interval has to be put down at the beginning of the first segment. Now either this interval fully covers the segment or it doesn't. If it does, then we move on. If it doesn't, then we need more intervals. And specifically, we need enough intervals to cover the distance between the endpoint and the current endpoint of our purple like frontier we have. And so this is just like a number and this is another number. So we can just kind of like figure those out. And then if all of our intervals are of size k, then we need the ceiling of y minus x over k intervals to cover that. Just more math. And once we do this, then we will continue. And otherwise, so that's one case. Otherwise, the interval fully covers the interval we put down fully covers the red one. Then either it intersects with the next interval or it doesn't. If it doesn't, then the next place to start this interval is at the beginning of it. And if it does, for example, say it's here, here, then there's no point in starting the interval at the beginning because we've already covered the beginning. So we can start it off later. And yeah, so that's basically the idea. So we start the next interval at the maximum of the starting position and the endpoint of the intervals we placed before. And then we just kind of do the same thing as we go along. It's kind of like math and stuff that happens. And then once again, for example, once again here you would figure out the distance from the endpoint of the interval you placed, the endpoint of the red interval to the endpoint of the interval you placed, possibly negative. If so, don't add negative intervals. And then this is y, this is x, then you need y minus x over k to do that. And then you just keep on going, keep placing purple intervals until you're at the end. Okay, that is the second problem. Now we on to the third. By the way, the stream isn't over. After this, we're moving on to the div 3, because why not? Okay, this is Painter's Duel, and so just write it out. So here you're given this triangle of a bunch of smaller triangles, and you want to figure out some of these triangles are possibly blocked off. You have two people that start off in different places, and you want to figure out, actually, let's say this person is orange and the other person is blue, then this guy can like move to paint, nope. This guy can move to paint each cell orange, and this guy can move to paint each cell blue. And the total score of the game is the number of orange minus the number of blue. So the orange player wants to maximize the score, the blue player wants to minimize it. Find the maximum possible score at the end of it, because the first player moves first. Or it's more like find the score of the game. Okay, well, I don't have intuition for this, but basically, if you like brute force all possible outcomes of the game, there aren't that many. And I guess the reasoning for this is all of these, the 3 cells in the corners, they only have one possibility of movement. And if you move into them, the game's like over, you're kind of done. And these cells on the edges, like these 3 and possibly more of them, they only have 2 possibilities of movement. And once you move into them, then you only have 1 possibility to move out. So it's really only like you have 1 possibility. So the only squares that have like a lot of possible things are the middle ones, and there aren't that many of them, I guess, or something. I don't know, something like that. And therefore, overall, there just ends up not being that many states, I guess. I don't really know. I don't know how you come to this. I guess it's just kind of intuition, like it just doesn't seem like there's that much going on. But, yeah, so essentially if you like literally brute force all possible ways the players can play the game, then you just like win. And it'll be fast enough, I guess. And so we can think about the possible outcomes of the game like this. So this is the initial state. Then the first player, orange, has a bunch of moves that they can make that lead to different states of the game. And we can think of all these states as different like vertices in a tree or something. Of all of these states, the first player wants to take the one that maximizes their final score. So what we'll do is we'll figure out the outcome for all these states. Say this is like -5, this is 2, this is 3, this is -7 or something. Then the first player is going to make the move that leads them to get 3 score in the end, because that's what they want. And the important thing about this is that this is a zero-sum game, which means that every point gained by the first player is a point lost by the second, and vice versa. So the first player is always going to take the maximum because it's not like the second player can help them out or anything. It's like greedy, kind of. But it's not exactly greedy. And we only get these numbers because we can figure out the outcomes of the game, right? So now for all of these possible states, now the second player has a move. And the second player wants to minimize the score. So if the second player ends up in any of these states, the second player is going to make a move that minimizes the score. And yeah, I'm going to do the div 3 after this. The stream's not over. The whole point is that I'm doing multiple contests. Guys, come back. Okay. How to write brute force? Well, like the state is that you have some cells visited. And I'm gonna get lunch before this though, in the middle of the round. Like the state is that you have some cells visited and some cells aren't, and then you have like the player that moves. So the brute force is literally you just like try all the moves and then you figure out which cells are visited and so on. So if the second player ends up in any of these positions, they're going to take the blue like branch that minimizes the outcome. And then of course here the first player is going to take the ones that maximize the outcome and so on. And at some points we're going to end with like terminal states where we'll call these cyan. And terminal states are the ones where both players have no moves. So we automatically know the score for terminal states. Like this is 7 or something, right? And this whole decision tree is eventually going to end in cyan. This whole decision tree is eventually going to still pick the wrong color. Is eventually going to end in all of these terminal states, and each of these terminal states is going to have their own score. So we kind of like do a DFS recursively, and then we use the terminal states to build up the maximum or the minimum score for this one, and then we use all of the cells on these layers to compute all the nodes on this layer, and then we use all of that layer to compute these ones, and then we get that to get the final one. And it's just like basically the DFS things. Yeah, so this is called minimax because the player on this layer wants to maximize the score. The player on this layer wants to minimize the score. Then this player wants to maximize it. And this player wants to minimize it. So there's a bunch of stuff you can do, stuff like alpha beta pruning, which basically lets you like massively reduce the amount of space you actually have to search through in like the average case. But it's not really necessary because this is fast enough on its own. You don't need any sort of pruning methods. You can just literally compute this entire tree and then figure out the outcome. And of course, these are all going to have terminal state. These are all going to have terminal states on there too. I just can't bother drawing them. So that's the idea. And yeah, okay. In terms of the code, is anything unclear about that? I'm going to go over my code, I guess, if you want to see how to do it, and then I can clarify stuff. So here's what the code is going to look like, basically. You have DFS, and throughout the DFS, you maintain this array like visited, which is basically if each cell has been visited previously or not. And then here, you figure out the move. So the first player has a bunch of moves they can go through. And by the way, I explicitly created a graph from this triangle stuff. So I turned all of these cells into nodes, and then I made a graph out of this because I didn't want to like be messy and do triangle stuff. So then all of these nodes would have edges like this and like that. And it's kind of a weird like graph with a bunch of hexagons. But like here, it's like you have a bunch of possible moves, then you just like try all of them, and then you take the maximum. And if it's the other player's turn, you take the minimum, but you still just try all possible moves. And then here, for all possible moves, you like go through. And yeah, if you understand recursion, then this should kind of be just an extension of that. You just figure out all possible things you can move to, and then you try all of them. And then if you don't really understand the principles of recursion, then I don't really know how to help. That's kind of a fundamental concept. I think there's a lot of stuff on recursion online. It's probably doable. But like, that's the basic idea. You just compute all possible states. The first player wants to maximize, the second player wants to minimize, so you do that accordingly. And when you reach a state where neither players can move, you compute the score and return that because that's the fixed outcome of that state. And the remaining outcomes is whichever move the player makes to minimize or maximize the score. And the final answer is like the root of this tree. It's kind of a weird way to think about things. I would say this concept barely shows up at all. Like, I've never seen it apart from this one. So, I don't know. I guess it's going to be fine. Yeah, Python is not great for recursion. I will say that. By the way, have you guys seen this? This is Gabe right here. He got 11th. It's like a madman. Okay, let's go over Yeatsy. As you can see, I had a bit of a struggle with this. But this actually uses a similar idea where there aren't that many like states to kind of try out. Yeatsy. Yeah, Gabe is definitely being hired by Google at some point. He probably won't even need to like interview. They're just gonna say, "Okay, Gabe, come work for us," and then just headhunt him as a college student or something cool. Anyway, okay. So there's a bunch of like stuff that goes Yahtzee. Yahtzee rhymes even more with that word. So that's probably actually why they called it easier. I don't know. I'm not going to say that word on stream. That's a terrible idea. I'm going to get like demonetized in the future. But yeah, okay. So basically what's going on here is consider some like positioning of groups where like there's the optimal configuration, like there's the final configuration of groups that the problem requires you have. For example, here you have 6 possible dice, and we say that 4 of these groups must have zeros, and the remaining 2, and we have to have another one that has 2. And then we have to have a like one other group that has 1 and one other group that has 2. And we're going to use green to denote the final state, even though it's actually like the opposite of what I did in the solving, because I don't know, I hate you guys. So, and then we have some like configuration of groups we currently have. For example, say we have 5 groups with size 0, and then 1 group with size 1. So the important principle is if the die lands in any one of these groups, then it's going to only help us, because it's going to get us closer to our goal of these final states. And also if the die lands in this one, it's going to help us because it's going to get us closer to our final state. So all 6 possible dice rolls are helpful, which means that we'll be happy with any dice roll we have here, and we can move on to the next one later on. However, if we have some state like this, let's say for example this is 2, then we're happy with any of these dice rolls because these will land us on 1. But we're not happy with this one because this one will increase it to 3, and we don't need 3, we want 2. So only 5 out of these 6 dice rolls are helpful. In general, for any state, there's a certain number of dice rolls that we'll accept, and then a certain number of dice rolls that we won't want to accept. And it doesn't matter the order in which we accept the dice rolls, because no matter what, we're going to need all of them anyway. And it also doesn't matter the numbers these are, because all of these numbers are equivalent since we have an equal chance of rolling them all. If the numbers were not equivalent, we would have a much harder problem on our hands, but they are, so we only care about the sizes of the groups, and specifically the numbers of each size we have. We can represent this as we have 5 zeros and 1 2. And then this will significantly reduce the state space we have. But anyway, so now, if we have a certain number of rolls that are helpful, let's call this x, and a certain number of rolls that, and like, we have m possible rolls, and x rolls of them are going to be helpful. So we need to know the expected value of getting a roll that we want. So let's denote this expected value as EV. It's some variable we don't know yet. So what happens? We roll the die. Okay. And this immediately costs us 1 roll, because a roll is a roll. So now so in terms of like expected value, we have an x over m chance of getting a roll that's useful to us. In that case, we're done. So we have x over m times 0, because we have 0 more rolls if we get a roll we want. And otherwise, we have a 1 minus x over m chance of getting a roll we don't want. And so the value for this is 1 minus x over m times what? Well, we're in the exact same situation. We ignore that roll, and so we roll again, meaning we kind of like, we're in the exact same situation. So this is actually still the expected value. Because if we get a roll that's useless to us, nothing changes. We're in the exact same position. So this is useful because now we can solve for expected value. So we can get rid of the 0 part. So EV equals 1 plus 1 minus x over m times EV. We can subtract this on both sides, and we can get EV times, this was initially 1 times EV. So 1 minus this, 1 minus x over m times is equal to 1. this cancels out to just EV times x over m is equal to 1. And so EV equals m over x. And what this signifies is that at any point, if we have x groups that we're going to want, like x dice rolls that we'll accept and m dice rolls in total, then the expected number of rolls we require to get a roll that we'll expect is m over x. Now that's useful. Because if we're at a state, then we can find out this value of x relatively simply. Actually, not relatively simply. But it's kind of like, of all these groups, like of these 2's, we can sort the final array. And then we can say, of the last, like, one group, is there something bigger than 2? And if so, then increasing this number, or one of these 2's, will help us. Because we can get, there's a higher number that we want eventually. And similarly, in this situation, we already know that this 2 is going to become this. So when we're considering what these 1's are going to be, like, we already know that they can't become this 2. So these 1's can only become this, one of these 5. But we have a number that's greater than 0 in this, specifically it's 1. So if we roll a 0, then it's going to help us get to this 1. So the condition for, like, a specific group size being helpful is that in one of its possibilities, it has to be greater than that group size. Like, otherwise, there's no point in making that group. It's going to be higher than we want. Okay, now, once we do roll a useful roll, then like, we have proportional probabilities of, like, the roll being, like, one of the group sizes. Specifically here, we have 5 out of 5 possible outcomes, and here we have 0 out of 5 possible outcomes of this being useful. So, like, I mean, the useful roll has a 100% chance of being a 0. Then once we get a 0, like, all of these are equivalent, we don't care which it is, so one of these zeros is going to change to 1, and then now we have to solve for the state where we have a 1 here instead of zeros. So, kind of formulaically, I can scroll, cool. Kind of formulaically, let's say f of s, let's say f of s equals EV for the state s. Now, f of s is equal to the value of x over m, where we can compute the value x by that. It's the value of m over x, as we've just shown down here, because this is the expected number of moves to get something useful, so we can move on to a new state. And actually, let's start with this. F of the final state is 0, because we're already there. It takes no more moves to get to the final state. F of the final state is 0. And f of everything else is m over x, the number of moves it takes to get to a useful move, plus the sum of... Okay, now this is where it kind of gets sketchy. For each group size G, let CG be the count of, like, the number of groups we have with size G. And we like mandate that G has to be useful, because there's no chance of us ever accepting a non-useful group size. So we're going to say that all of these group sizes are useful. And again, useful means that it will help us make progress towards the final state. So It's the sum of G over all useful group sizes. And it's G over X, which is the probability of the useful role being this. It's like the probability of rolling G. Well, actually, first we factor in the time it's going to take for us to get a useful role. So we've already considered that we're going to get a useful role. And so therefore, we only have to consider X because we only have X possible useful roles. We're not going to assume we have any other non-useful role because we've already taken that into account. So now the number of possible roles we have is only the useful roles. And therefore, this is G divided by X and not G divided by M. So it's G divided by X because that's the probability of getting this, times F of the state where you roll G. And of course, this affects the state by changing one of the group sizes. So that you can kind of just do out with implementation. You just you lose 1, 0, and you gain 1 of the next group size. So this is the final formula, kind of. And yeah, I'll let that sink in, I guess. That's kind of what this is. Hopefully that was clear. But, okay, this is the formula for the answer. So if we can make these states efficient enough that we can do this, that's cool, and we'll be good. And we can also memoize these states, which means that we don't ever recompute one of these again. And the way we do that is, well, the state is a set of pairs of group size and count. So we can use something like a map, or like a hash map, or a tree map, or an ordered map, whatever it is in your language, program language, we can use a map as a state. And then we can use another hash map or something to memoize these, and we can hash these maps into some numbers. And then if we ever visit a state again, we can check if we've already seen that hash, and however a hash map works. We can check if that element's already in the map, and if so, then we already know the answer, so we can return that answer instead of recomputing it. So the final question is, how many states are there? And why does this not TLE? Because there could possibly be a lot of states. This is just a straight up brute force kind of. And I don't have an answer for you, but clearly there aren't that many states because my solution passed very quickly. But the question is, how many states are there? An upper bound on the number of states is it's an upper bound on the number of states is what's up, Ayush? An upper bound on the number of states is where we have, say our final groups are like this. We're going to ignore all the zeros. So we have 3, 7, and 10, for example. Then if we kind of, I don't know how to explain this, but it's we'll have 3 groups here. We can have any number of groups that are less than 3. Then we have only 2 possible groups that are less than 7, and only 2 possible groups that are less than 10. So it's kind of like any number in this range from 0 to 3 has 3 possible groups. Then any number in this range has 2 possible groups, and any number in this range has 1 possible group. G over X is the number of useful states we have. Where a state is useful, or sorry, a number of useful roles we have. Where a role is useful if, when we take this role, it will help us get closer to our final goal. And that means that if a roll is useful, it won't lead us to like some invalid state where we'll never reach the goal. It will instead help us. So for example, rolling a 0 is useful here because we want a 1 eventually, and rolling a 0 will help us get closer to that. But rolling a 2 is not useful because we've already filled in like the 2's. I will leave the computation of useful states as an exercise because it's like annoying. It's like kind of an upper bound, I guess, is like the size of like the number of 3's we have. So it's like 3 times 3 times 3 times 2 times 2 times 2 times 2 times 1 times 1 times 1 or something. And there's some stuff going on here. And there's like a lot of different there's a lot of different worst cases, I guess. Actually, I don't think it's the product of these. No, it's more like the sum of these, actually. Honestly, I don't know how to explain this. This is like a very complex complexity analysis. Maybe the editorial has something for this. Let me see, actually. Okay, so they say it's about 1 million. Something like that. Okay, so the editorial says there's about like 1 million states or something, and our computation isn't that bad, I guess, so it passes pretty much. That's the idea. Kind of interested. What does the editorial say about this problem? Memoization, alpha beta pruning. Nice. Now you should alpha beta. Don't you like alpha beta? Isn't it fun? It's like the best algorithm. But yeah, there are like a lot of these, so I don't know, I guess the number of states is just small for both of these. I don't know how, like, I figured out the number of, intuition, the number of states would be small for this one, but not for this one. So I don't even know. It's kind of like, you do something like there. A lot of states end early, I guess. Yeah, alpha beta is OP. Kind of interested, what did Gabe do for this? Did he just, like, brute force it, too? Actually, whatever. I'll figure that out later. Okay. So that was Kickstart. I just went over all the solutions to that. If anything was unclear, ask in stream or comments. Okay. So I think now the plan is to like... So as I said, I was going to kind of like do a poll on what you guys would want to see. And so the next best one was the div3, which means we go here. This is basically the plan. So, yeah. That's what's up next. We're going to do the div3. Before that, though, it's like 1 a.m. here, so I'm going to take a slight break, probably get some lunch. Something like that. I'll be back in a couple minutes, I guess. So what I can do right now is I'll mess with the stream. So, since we're changing the stuff. And we can do that, stick that here. And I'll change the thumbnail to this. Okay, I'll be right back. And then after that, we'll start with the div 3. I'm gonna mute my mic. And if I seem like I'm doing stuff but I forget to unmute it, please tell me, because that's happened before. Okay, we're back. And let me read chat. Anything I missed? A, B, C, D is pretty basic. Do E, please. I mean, I know I could, but like, look at this. D has 2,000 solves. That's like almost a fifth of the people who've solved A. So there are going to be many people who are probably interested in seeing that solution. Thinking beyond just the stream, like the post video that people might want to watch. It could probably be helpful to just go over everything. But I will get to E. Thumbnail's fixed, right? Here's what I'll do. You guys, how about this? You guys want me to do it backwards? I can try that. Say the word 22 in chat if you want me to do it backwards. Also, is my mic unmuted? Yes, it should be. Anyone else for doing it backwards? I will start in 2 minutes so I can set the stuff up. There's nothing to set up. Nice. I'll look at chat. Right, everyone. A large majority of people. Oh, and say 15 if you don't, but it doesn't seem like anyone doesn't want me to, so that's fine. So 22 if you want me to do it backwards, 15 if you don't. Kind of like a Twitch poll. Alright, we're pulling a rainbow. Let's do it. $22. Nice. Approximate Codeforces ratings for C and D. I honestly don't know. I don't think these problems would appear on Codeforces. Like, no coordinator would ever accept this, I hope. 12? Oh, come on. Not 15. Okay. Well, we're doing it backwards. Let's go. Number of subsequences. Oh boy. Given a string S consisting of all lowercase. What? String S, lowercase Latin letters A, B, and C, and question marks. Okay. Fun. Number of substrings A, B, C. Okay. So, what's with that? Alright, the decision's made. You don't have to say numbers anymore. Let's just read the input. Move paint to the side. Just obligatory check if we're still recording, even though you guys are talking in chat, so that's hopefully the case. Okay. The maximum number of contests I've done in a day. I don't know, it's probably been like 2, I guess. I would do more, but I like have other stuff to do today, so I can't do it entirely, but something like 2. I don't remember. Okay, so N is 200,000, which means stuff is big. Okay, so let's say the string wasn't fixed at all. Let's say it was like A, B, A, C, C, B, A, C, I don't know, whatever. All right, so what we do is we can store different things. We can store the count of empty, no, that's stupid. We can store the count of just A's we have. Then we can store the count of just AB's we have. Then we can store the count of ABC's we have. Now, if we encounter an A, then neither of these counts are affected, but we get +1 to A. plus 1 to this. Then when we get a B, we don't get plus 1 to this, but what we get is we can put a B at the end of all possible A's we have. So what we get is plus the number of A's. And then similarly, when we get a C, we can stick that onto all subsequences AB, so we add the number of ABs. But when we have a question mark, what we really want is, over all strings, the sum of all possible A's, the sum of all possible B's, and the sum of all possible ABCs. So I think it seems like it's just kind of the same thing. Like, when we have a question mark here, for example, either we have an A, a B, or a C. If we get an A, we add 1 to A. If we get an AB, then we add the count of A to the number of ABs. And if we get a C, then like we add the number of ABs to the number of ABCs. But like we can get all of these, and we're like interested in the sum of all of them. So I think we literally just do like all of them. That feels like it should work. Okay, so CAB. Let me just do like this, like just the counts. And then we'll just copy this in. So now CA mod is 10 to the 9th plus 7, right? Okay, then else if SI CAB equals CAB plus CA mod, else if SI is equal to C, CABC equals CABC plus CAB mod, else, then we have a question mark. So we want to do these in reverse order because we don't like, if we did these in like order like this, then what would happen is we would like imagine having an A here, and then we would have a B in the same position, and we don't really want that to happen. So let's not do that. We do it in reverse order to make that not happen. And that's kind of it. Test cases. Eight. Okay, what? Maybe there's something else I'm missing. Oh wait, okay, there's a bit more we have to do. Because when we get like all of these strings, then I guess all of these are multiplied by 3 somehow. What do we get for this? How far off are we? 35. What are we off by? That's kind of weird. I think it's like this. So actually, when we have, that doesn't make sense. No, yeah, it does. Okay, so of the 3 possible strings, A, B, and C, let's consider what it does to all these counts. So I kind of messed this up. C, the number of ABCs is the same for these 2 strings, but we have to count both of them. So it's 2 times the original count ABCs, but this one gets the original plus however many ABs we have. So it's ABC plus AB, which is the equivalent of 3 times ABC plus AB. And AB is the same thing, except it's like, so A, B, C. If we have an A or a C, both of these are the same, and if we have this, then it's like it's 3 times AB plus A. These are terrible letters, sorry. And then for A, it's 3 times A plus 1, I guess. I think that's how this works. Indeed it is. What? That's a bit messed up. See if this one's wrong. Okay, this one's wrong. And why is that the case? What else am I missing here? So if we get a C, the sum of all CABC is like different, I guess. What's going to happen here? With AB, something's messed up. It's like these are added or something. No, because we can't not add a character, so we have to add one of A, B, or C. And if we add one of A, B, or C, then we're like doing stuff. This is F, by the way, going backwards. And yeah, something is messed up here. What's the answer for 4 question marks? We can get a lot of things. So this should be still be 1. Should still be 2. Because we can get BC here and A. I'm not going to become LGM, not at this pace. Something's messed up here. So read into N and the string itself, then. So if it's A, make it 1. Otherwise, if it's B, then we get a bunch of extra ABs. Otherwise, we get a bunch of extra ABCs. And if it's a question mark, then we get even more stuff. I'm struggling on F, not just doing F. Where does this first go wrong? The plan is to struggle on all these problems. Maybe I oversimplified it or something. Wait, this should be... Does this fix it or does it make it? That does not fix it. Okay. What does it do to this? What I'm thinking is like... Okay, I got it. I figured I was wrong. So, the other two transitions were right, but the problem with A is that when we have some number of strings, like this, where we can extend some A here. Yeah, please don't give spoilers, although I didn't read that, so it's fine. Like, we can extend it, we can slap an A onto the end of all of these strings, like any number of strings that we want. And the number of strings that we want is like 3 to the number of question marks we have before this A. So we don't just only have one A that we slap on every time. We can slap on an A for every possible string we could have had before this. So this should also be here. And I think that will fix it. Zero. Okay. Now the only problem we could have here is if we're doing mod wrong, and that would be stupid. Cool. How are we doing? Nice. Oh yeah. Alright, let's do E. Just write E down. Okay, rock, paper, scissors. Game consists of several rounds, each round is independent of each other. Each round, 5,000th place ores. One player showed rock and the other showed scissors, and the player showed rock. Okay, rock, paper, scissors. Sure. So rock beats scissors, scissors beats paper, paper beats rock. I feel like I've seen a problem like this before. I feel like I've seen this exact problem before, something like this. But I don't remember it, so... It's the minimum and the maximum number of rounds Alice can win. No, it's not hoof, paper, scissors, it's something else. It was some other Codeforces round, I think. Although I'm not sure. I have solved hoof, paper, scissors, though. That's also something. By the way, I think we have a lot of new viewers, so you should subscribe. Yeah. What's happening here? So let's say we have like a lot of it's a bit like that ActCoder round, or that ActCoder problem where we got like, I don't know, it's kind of weird. Yeah, I just blatantly said subscribe. Because we'll do a lot more stuff like this probably. Okay. How do we work this out? So let's just like focus on the minimum for now. For every, let's take this sample, like 011110. For all of these, how does this work? It's like this beats this, this beats this, this beats that. Yeah. So for all ones, we want them to like not match with zeros. And for all of the, no, it's not flows. For all of these, we want these to not, is it flows? Could this be done with flows? I really don't want to do it with flows, so it's not. We want these to not match with this, and we want these to not match with this. So automatically, we can get away with not matching the minimum of these numbers. By like, we can kind of like greedily, like let like x be the minimum of all of these numbers. That we can just like put x of each of these in something that doesn't win. And I guess that does something, but it's not that much of a something. So this one can match with either of these two. And this one can match with either of these two. And this one can match with either of those two. All right, so guess what we kind of want is, I don't know what we want. I'm pretty sure like the answer is going to be some cyclic shift of these operations if we like put them in order, but other than that, it's not that clear what's going to happen. So I don't know. If we put as many of these to, so if we put as many of these to here as possible, and then as many of these to here as possible, well, it's kind of like the balance. How many of these do we want to put in here? You know, it is actually kind of, I think, it might actually be solvable with flows. It's actually maximum matching. Oh my god. And minimum matching, I guess? It's genuinely maximum matching. Okay, actually maximum should be easy to solve, I think. Maximum should be easy to solve if we have like A, B, C, D, E, F. Then we can like win the minimum of these two, we can win the minimum of these two, and we can win the minimum of these two. So we can like, I think the maximum is simple. The minimum is the hard part. Or so it seems. Let's just test it with these tests. What? 226, 3, 15. Okay, so we have the maximum, right? Now we'll do the minimum. You can do flows on this. You can. It's possible. So the maximum is simple. Basically, if you assign all of these together, like you can win minimum of A and E moves because like you have that many that you can match together. And then you don't really care what happens with the other ones. You just put them wherever. And then you can also win the minimum of B and F moves because you can match them together and you don't really care about the other ones. Because you know all of these, both of these arrays in total sum to n, so you can eventually make the other matches. And you can win the minimum of C and D moves. And you can't win more than the minimum because like you only have this many rocks or whatever, and Bob is only going to play this many scissors. So the answer for max is the minimum of A and E plus the minimum of B and F. Move this over. Plus the minimum of C and D. Now we handle the minimum. That part's more fun. What do we do in this case? We could genuinely solve this with flows, you know. We could. That would be so easy. We could just be done with this problem. We would solve it with flows, it would be like maximum matching, would be done. It'd be perfect. But I don't think you guys would want that, so let's not. What is going on here? So some stuff is going on. We have it. We can move A to both D and F. We can move B to both E and D, and we can move C to both this and that. And we want to, now we want to minimize these numbers of matches. I probably would actually, because that would be the easiest thing to do. Like flow is templated, so I could just copy in a max flow struct and like set up 3 edges or 6 edges and be done. I think it would genuinely be easier than thinking out this casework. But I'm not going to do that because we're on a stream and I have to like respect that many people don't know flows. Yeah, like the flows thing is just the first thing that comes to your mind. Like I can search up BenQ's template, and then that's it. Just copy this in. That's how easy it would be. Yeah, wait until I solve it, probably. I mean, I don't know if stuff would work. So basically we have these like masses of stuff. So A can feed into two things. It can feed into D and it can feed into F. B can go into D and E. And C can go into E and F. Oh no, sorry, B can go into D and E, C can go into E and F, yeah. So if we model this like a graph, then we get A can go here, B can go here. Oh, this is terrible. B can go here, and C can go to here. And this is straight up maximum matching. This is how you would set up the flow graph. Like, is this, I don't know if this is a representation that will help us solve this. What's the answer, like, for these? Oh, I don't know what this is. Okay. I think what we're concerned about is the maximum of A, B, and C, and the maximum of D, E, and F. Wait, that doesn't even make sense. That doesn't make sense at all. Oh yeah, C would be to E and F. That's true, but it doesn't really help. It's kind of like, how many of these are we forced to make? And we're only forced... Oh, wait, okay, I think I see. We're only forced to make some of these moves if A plus E is greater than N. Because otherwise, we can put all the A's on one side, and then we can put all the E's on, like, the other side. And then, similarly, we're only forced to make moves if B plus F is greater than N, and C plus D is greater than N. So I think what it is... like, it's A plus E minus N. I don't know, maybe this is wrong. This should be max, actually. 1 second. It should be max because we want to round up to 0. And basically the reason I think this works is because if none of these are greater than N, then we can kind of like cyclically shift all of these, and then we can make it in a way so that, like, for example, all of the A's are over here. And then we don't want to match them with any of the E's, so we can put the E's over here. And we have enough space because these don't sum to N. Then we can put, like, the B's over here, and then we can put the F's anywhere else. Like, as long as it doesn't match with B's. For example, here. And as long as these don't sum to N, then we're fine. And then for the C's, it's kind of the same thing. I think that's the idea. We'll see if I'm right. Nice. What? Oh, wait. Oh, it should be B. Okay, that works. Yeah, that's the basic idea. That if none of these are greater than n, then we can cyclically shift the rocks, papers, and scissors to like not overlap, kind of, and then we'll be fine. I guess it's not exactly a cyclic shift, but it's kind of the same thing. It's kind of a weird version of it. Actually, we'll cyclically shift by the maximum of all of these, and then we won't get any overlaps. And otherwise, we're forced to have some overlaps, but we're only forced by the one that sums to greater than n, because there's only going to be one of these three that sum to greater than n. And in that case, that's the amount that we're forced to win. Okay. That was wacky. How are we doing in the virtual? Are we beating the... Hey, our place went up. Nice. Good job, us. I'm going to do more formal solutions after the end of this. But for now, I think we're fine. Let's do D. So we have an integer array, A1 to AN. It can have positives, so it can't have zeros. Even such a huge that they can't be represented in most standard programming languages. Okay. Okay, this is relatively standard. Here's the basic idea. Well, because what about ties? Ties, Alice doesn't win either. If there's a nice way to handle ties, then I guess that will work. But we can't just like, it's not the complement. This is in response to why can't we maximize the games Bob wins. Okay, so basically here's the idea. If you have any array, then like 1, -5, 3, 2, then consider like the prefix sums of the array. So for example, the sum of the first I elements. Notice that when we have this, these two elements are going to have the same prefix sum, which means that if there's a subarray of sum 0, we will have encountered this prefix sum before. This is like by nature because the difference between these two prefix sums is the sum of this subarray. So if the prefix sums are the same, then the sum of the subarray is 0 because the difference between the two prefix sums is 0. So as soon as we get any sum of the subarray with 0, we know that this is the leftmost index that has a sum with 0. So what we can do is we can insert like some huge infinity number like right here. And then this subarray is going to be broken up by this infinity. So then now we kind of like have a barrier here. So now we solve the exact same problem, but starting from this subarray. And then we just do that, and we insert an element whenever we need to. Plus ants, then yeah, huge infinity. Okay. Do we want to also increase the counts of 0? I don't think we do. I think we just do plus plus counts psum. Oh, I need these elements 0. Okay, no. What happens with ties if you maximize the amount of game Bob wins? No test cases? Wait, are there test cases? There are not test cases. Oh, I should read the input. Ah. Four. Why is that wrong? Does this fix this? Does not fix it. Okay, what's with that? Oh wait, I should reset the prefix sum. Wait, does that matter? Doesn't matter. I feel like it shouldn't. Any reason I use map? No, not really. I'm just more comfortable with map because unordered map, there's like the chance of being hacked and stuff. And especially on div 3s where there's a hacking phase, it's just like not worth the risk. By the way, Gabe, how did you solve the fourth problem from Kickstart? Was it like a stupid brute force where you just like do math? Or was there actually a smart way to do it? Guess the answer is plus plus counts. Okay, then once you get to this point, you can both take this array, including this element, and excluding this element, which means that here the prefix sum will be the sum of these elements, and here the prefix sum will be the sum of these elements. And when you reset the prefix sums, because you have this infinity here, you have to take into account both of these. That's what I'm doing right here. Hey, we're getting better. Let's go. We're almost at 3 digits. Okay. You have the array A consisting of 1 elements. Increase some single element of A by 1, or append the copy. Okay, here's my idea for this. So you have some number like, nope. Say you have some number like this. So you have 1 initially. So say you increase this to 2. And then you copy this, so you create a copy of 2. But then you increase this by 3. So now you have the elements, 2 and 3. You can think of the array like these vertical elements. Actually, I think a better way to do this is horizontally. So you increase this to 2, then you create a copy here, 2, and then you increase this one to 3. So now your current array is this 3 and this 2. But what if you just like reverse these? You just you first increase this to 3 and then copy it. Then you're just going to be strictly better off because you're going to have like a higher number. So the optimal thing to do is what I think is first do all the increasing operations on the first element, then do some copying. And okay, so that's basically the idea. And I think the optimal, so we're going to pick some number x. We're going to do x minus 1 . We're going to do x minus 1 copy operations, or x minus 1 increase operations, so that 1 becomes x. And then once we do that, we do, what was it, ceiling? Yeah, the ceiling of n over x increase operations, or multiply, like copy operations, minus 1 to get the sum n. Which is equivalent to the sum of, no, it's not. That's it, right? Wait, is that, like say you have 3 and then 5 and the ceiling is 1. Am I doing this wrong? I think it shouldn't, wait, this just seems wrong. Okay, the amount you need to increase is m minus x. The amount you need to increase is m minus x. And I'm messing this up somehow. And you can do it by, okay, so it's the minimum k such that kx is greater than m minus k, which is x, m minus x. So k equals, yeah, ceiling m minus x over x. That's right, right? Yeah, yeah, it is. Yeah, it is. It is. Indeed, it is. It's like, this is the same as n over x minus 1, which I think is more appropriate because this could have troubles because like C++ rounds towards 0 instead of rounding like based on the number line, so it's going to be different. So it's better to have this be strictly positive, and then we'll just subtract 1. If we have 7, we need 3. If we have 6, we need 2. So it's ceiling. Okay. Yeah. So basically we have this function. We have x minus 1 plus this thing. So we get a form of like we get a function that's like kind of like O of x plus n over x. It's like around that, right? So general mathiness says that the best way to optimize this is with square root n. But like we don't know exactly how close to square root n we want to get. So what I'm gonna do is I'm gonna try all numbers on the interval of square root m minus 100 and then square root m plus 100. And that's just gonna work, I think. So LO ants equals n. We can start off with a baseline of n minus 1. Then if I is greater than or equal to 0, because we have to increase at least once. Yeah. Then ants equals min ants I minus 1 plus n minus n over I minus 1. It's maybe off by 1, I don't even know. Or it's gonna crash. Wait, oh, it should be I is the value itself. Yeah, so this is the value itself, not the number of increases. So I should not be able to be 0. Why? Oh, because we have multitest now. Huh? Zero, 2, 11. What? Come on. Oh wait, this should be ceiling. So n plus I minus 1. Ceiling of that. Okay. 03, 11, 72. Yeah, okay. Oh, what's up, Leor? What, 0 milliseconds? What? Are we triple digits? Hey, we're triple digits! We're doing so well! Look at this! Okay. N types of, oh my god, this is such a long statement. N types of tiles, n times, 2 times 2. Each cell of the tile contains one integer, infinite number of tiles of each type. Symmetric with respect to the main diagonal. What? Why? This main diagonal matrix in each cell of these square has to be covered as exactly one tile cell, and also sides of tiles must be parallel to the sides of the square. That's so weird. M times M. By the way, I'm actually 47 years old. So my voice is so deep. Okay, so the way this works is, I guess, this is so weird. Like we have a square, and then we have a bunch of, this is not a square. We have a square, and then we have a bunch of 2 times 2, like, sub-squares we can put. And basically, if we, like, flip this half onto this half, it has to be the same. That's what the symmetry means. So if M is even or odd, are we just, like, done? Is that not possible? I mean, if M is odd, tiles can't overlap and they can't, yeah. This is so weird. So this is one test, then this is the next test, and M is odd here, then 1, 100, then 1, 2. Okay, so here's the way this is going to work. We have to put some, so first of all, if M is odd, then there's just no answer, because we have 2 times 2 cells. Otherwise, M is even. So we have to put some of these squares on here, right? So we have A, B, C, D. Now we don't really care. So what's going to happen here? Well, if this matrix is going to be symmetrical, we don't really care about A and D, but B has to be equal to C. And so we put a square here. Then it has to match with the square here. So let's say it's W, X, Y, Z, and now we're going to call these A, B, C, and D. So A has to equal W, B has to equal Y, C has to equal X, and D has to equal Z. And so if this is just true, like if we can find two tiles that are like complete inverses of each other, then we can just put them like everywhere. Like we can just put W, X, Y, Z here and A, B, C, D here, and just like keep going. Or we can have a single tile where X equals Y. Where X equals Y. Then if we have a tile where X equals Y, then basically here we'll put W, X, Y, Z here, and we have the W equals W, Z equals C, X equals Y, Y equals X. So if we have any tile where X equals Y, then we can put that everywhere. Or if we have two tiles that are inverses, we can put those everywhere. And actually, no matter what, we need a tile with X equals Y anyway, because we need to put stuff here. We can't put inverses on this diagonal. We need X to be equal to Y here. So I think that's the only condition, actually. We just need a single tile with X equals Y. Maybe I'm wrong, kind of rushing into this. If so, we'll figure it out. What? Oh, wait. What? Oh, seem to end M. Yes, no, yes, no, yes, yes. Okay. Works for the sample. Guessing it'll work everywhere. Nice. How are we doing now? 151st. Nice. Okay. Let me try and blitz through this. Let's see if I can finish in under an hour. So NX. First floor contains 2, every other floor has X. What? Nice. Okay. Sorry, I just wanted to finish in under an hour, so I went kind of silent there. Where are we right now? 52nd. Nice. Although I think as more people start to solve E, like look at this. This guy has 74 penalty. If he solves E, he's going to win. He's going to beat me. So right now this is our place, but it's definitely going to go down later. How do my friends do with this? Anton, nice. And other people have yet to do stuff. Okay, so that's that. Alright, let me explain what just happened there. So So either whoever it is, either Petya is on the first floor or not. So the first floor has numbers 1 and 2. The second floor has numbers 3 to x plus 2. The third floor has numbers x plus 3 to 2x plus 2. So first, special case, if I don't know why would they do this? So let's say n, we have numbers n and x. So if n is less than or equal to 2, then we're just on the first floor. Otherwise, we can subtract n from 2. And then now we're dealing with, we can subtract 2 from n. Say set n to n minus 2. Then we're dealing with the floors 1, n, and then n plus 1 to 2n, and then to 2n plus 1 to 3n, and so on. So if Petya is on the ith floor, then that means that I times n is great. No, wait. I times, sorry, this should be x. All of these should be x. 2x plus 1, 2x, 3x, etc. So I times x must be greater than or equal to n, and we want the minimum such I, so it's just the ceiling of I over n. And then plus 1 because this is the second floor, this is the third floor, fourth, etc. Wait, sorry, it should be I is equal to n over x. All of that was wrong. Like the entirety of that was wrong. So I is equal to 1 plus n over x. That's the floor we're on. And so that's kind of what I just did. Subtract n minus 2 and then ceiling. How far is my place dropped in these in this 3 minutes we've spent? We dropped 4 places. Nice. Was this the last thing on the list for today? Okay, well, the other thing I had in mind was @coder. @coder is possible. This was the other one. It didn't get as many votes as these, but I mean, it's possible that I can do that. That's the last thing I would do for today. I kind of don't want it to take that long, though. So let's see if it, how hard was it? Specifically, how hard was the last problem? It has 68 solves out of... Okay, this was hard. I might not do it then. Yeah, okay, I think if I try this, it's going to take too long. And I do have, like, other things to do today. So I think, yeah, that's going to be it for today. But we were productive today. We did the kickstart, and then we did this rather quickly. I think it was good. Yeah, we'll just leave it at that. Okay, I will finish the stream soon. You can chat for a bit. I'll read the chat again. Actually, I can, first I'll formally go over the solutions. This is going to be hell of a pain to timestamp. I'll formally go over solutions. Actually, is there any solution that wasn't clear as I did this? I guess it wasn't that bad. Yeah, I'll just leave it at that, actually. I think it's good enough. You want to do type racer? Oh, come on, I can't play this. I don't know how to type. What makes you think I'd be good at typing? Actually, we don't need to stream type racing. We can do that off stream. Look, you don't have to humiliate me publicly. You can humiliate me privately. All right. I'll end the stream here. We'll like do it like somewhere else. Okay. In that case, that's basically it. That was the stream. Hope you enjoyed. See you guys. This should update. Like, YouTube's gonna take a while to upload this video, so I'm not really sure why, but it will. So this should be up by maybe tomorrow or something. So if you missed a bunch of this, you can come back to it later. Okay, that's basically it. Goodbye.